In previous lessons, we looked at the early history of the universe, from the Big Bang through the production of subatomic particles that then assemble into atoms. And remember, when atoms formed, then the light at that stage was sort of released, set free, and we detected that as the cosmic background radiation. And then gravity is going to condense hydrogen and helium to form the first stars. And those stars will gather together under gravitational influence to form the first galaxies. But at this stage, we don't have any planets yet. So in this lesson, we'll look at where planets come from. And we'll see that stars produced the materials to make planets. Let's recall what stars are doing. They're doing nuclear fusion. So gravity will condense a cloud of hydrogen to such high temperatures and pressure that hydrogen nuclei, protons, will fuse together to form a helium nucleus, and that releases lots of energy. And then the pressure of that fusion reaction sort of pushes back against the force of gravity, and you get a stable star. But for our purposes, what's really interesting that is happening inside stars is stars are forging new kinds of atoms. Stars are atom factories. So we drew it like this. Inside stars, stars are fusing together nuclei to form heavier and heavier elements. Recall, an element is a substance made of one kind of atom. So here we have lithium, beryllium, boron, carbon, nitrogen, oxygen, all these different kinds of atoms with different numbers of protons and electrons. They are forged inside stars. And when stars explode, they can make even heavier elements. Here we see a diagram showing the formation of stars and then what happens as they run out of fuel. So here we have the cloud of gas that will condense to form a star. And the star will undergo nuclear fusion in its core. It'll be making heavier elements like carbon and oxygen and nitrogen and iron and silicon, etc. And then, if it's a big star, it runs out of fuel, it will explode in what's called a supernova. So all of the elements made inside the star, as well as the force of the explosion creating new elements, all of those new elements will be dispersed back into space. So we have a situation where new stars will explode, produce heavy elements that then get mixed with more hydrogen and helium gas that can form a second generation star, which can go through this process again, supernova, making even more elements. You go round and round the cycle with 3 generations of stars, 4, 5, 6 generations of stars, and you start to now enrich the interstellar space with heavier elements. So just a reminder, an element is a substance composed of a single kind of atom. So most of the elements here on the periodic table of the elements here, they were forged in stars or in supernova explosions. The Big Bang itself produced hydrogen, some helium, and maybe a tiny amount of lithium. So early on there were just stars, and stars are the ones that produced all of these other kinds of atoms. Now this is a picture from the Hubble Space Telescope, and this is a nebula. So the scientists would describe this as a giant cloud of gas and dust. Well, interstellar clouds of gas and dust are the nurseries for new solar systems. The gas is mostly hydrogen and some helium, and the dust is composed of molecules that formed in space. Recall the heavier atoms that were created in and ejected by stars. What they did then, as they were out in space, they bumped into each other and they chemically reacted to form more complex molecules. We can think of this as sort of space dust. So back to the picture here, all of these kinds of atoms then, they have electrons in their outer shell, and it's as if atoms are trying to fill up their outer shells. So under the right conditions, atoms can form chemical bonds between each other and different kinds of atoms, and then you'll form molecules. So out in space, as stars were ejecting all these different kinds of atoms into space, the atoms linked up. They formed chemical bonds, forming molecules in space, and that's what this dust is composed of, molecules. Here's a famous cloud of gas and dust, the pillars of creation. Again, a picture taken by the Hubble Space Telescope. So we want to think about these clouds of gas and dust as regions where new solar systems can form. You see, if it's just a cloud of hydrogen, all you can get is a star. But if it's a cloud of hydrogen and this dust, these heavier elements and molecules, then you can get a star with planets, rocky planets like the Earth. Here are some molecules that have been detected in space. So they're fairly complex molecules, so we can get some interesting chemistry going on out in space. And if we ultimately then think that our solar system, including the Earth, was formed from these giant kinds of clouds of gas and dust, then the atoms that make up our bodies were actually once distributed in giant clouds, as you see in the picture. So what can a cloud of gas and dust do? Well, that cloud can make a solar system. In the upper left, we see the cloud of gas, mostly hydrogen, but it's enriched with heavier elements and molecules, the dust part. And gravity then can start to compress this cloud. Sometimes a nearby supernova, the shock wave from a supernova, might trigger the process. But if you get gravity operating on this cloud of gas and dust, then you're going to get a star in the middle of this cloud. As the temperatures get so hot and the pressure so great, you'll get nuclear fusion. The star will be here, but the heavier elements then will be left orbiting around the star. And those heavier elements, those molecules, will assemble into smaller particles, and then gravity will assemble them into larger particles, and then small rocks, and then larger rocks and rocky bodies and planetary bodies, and pretty soon you have planets. Now, that process may take tens of millions of years, but that's the idea of how solar systems form. We drew it like this. We have a supernova shock wave going to trigger the condensation of a cloud of gas and dust, forming the early stages of a solar system. The heavier elements are going to aggregate into smaller rocks, and then larger rocks, and ultimately planets. Now, we've noted here that the Earth is in the habitable zone. Now, what does that mean? Well, the habitable zone is an orbital distance where conditions are favorable for the existence of liquid water, and then possibly the chemistry that might sustain life. So here we see the Earth, and it's at an orbital distance, not too close to the sun, not too far away, where water can exist as a liquid. And why is liquid water important? Because living cells contain lots of water, and this is where the chemistry of life occurs. So if life is going to emerge on Earth, scientists believe that it was a critical factor that there was liquid water on Earth. Now, the early Earth was a very different place than it is today. It was an extreme environment with volcanoes, and the atmosphere was very different. It was a very sort of a toxic place. But scientists hypothesized that life emerged from geochemistry. In other words, the molecules that the Earth was made of, they continued to undergo chemical reactions. So chemistry on the early Earth produced important molecules that later self-assembled into the first living cells. So we go from a lifeless rock, the early Earth, to a rock with life, the Earth today. And that critical transition happened when the first living cells emerged on Earth. These cells, we can think of them, NASA sort of defines life as a self-sustaining chemical system capable of Darwinian evolution. So cells emerged on Earth, and then those cells are going to reproduce and change over time and create all the living things on Earth today. So when we think about our solar system with a handful of planets here, one of these planets really does stand out, our Earth. It's the only one that we know of that is teeming with life. And if we step back and think about why is there life on Earth and not other planets in our solar system, there were lots of conditions that sort of were favorable for the emergence of life on Earth. First, the sun was moderate in size and it was stable. Rocks and comets that made up the Earth had water to act as a later medium for chemistry. The Earth was in the habitable zone and fairly circular, so no extreme temperatures. Water remains liquid. And there was a large sampling of different elements made by stars that allowed for a lot of chemical diversity. So The early Earth, then, was a place where chemistry could produce a living cell. And that's an incredible story. And scientists are actively trying to figure out how that happened. So that takes us then, in our story of cosmic evolution, to the present day. We live on a planet orbiting a star, our sun, which is moving through the Milky Way galaxy. And the Milky Way is one of hundreds of billions of other galaxies in a giant universe. But on Earth, there is a species with big brains and is trying to work out the entire history of the universe. Pretty incredible story.